4, which is to talk about neural integration and the process of basically analyzing what's happening on a neuron. This happens at the axon hillock, okay? And this is basically wrapping up this process and talking about how we analyze whether or not that second neuron fires another action potential. And there are a few processes involved. We're going to talk about summation. We introduced this concept before, this ability of synapses to sum either in space or in time. We're going to talk about frequency coding, which I kind of talked about earlier, right? Regulating or influencing the different stimuli using different frequencies of action potentials. We're going to speak about divergence and convergence, which are different anatomical arrangements of neurons. And then we're going to speak about the axon hillock a little bit as well. Okay, so we know an action potential which is triggered. It's going to be triggered at the axon hillock, and then it's going to propagate down the length of the axon. We know that in order for an action potential to be fired down an axon, the stimulus must get to threshold. What is our threshold value? What's our threshold value in terms of a membrane potential? -55, thank you, -55. So our graded potential gets to -55, and so we must fire an action potential and it propagates down the neuron. If the potential does not get to threshold, this will not result in an action potential, okay? And I've said that several times, very important to understand. This is all or nothing, either action potential or no action potential. Let's look at divergence and convergence. So we've been speaking about two neurons pretty much communicating in series. We talked about a presynaptic neuron and a postsynaptic neuron, and the way we've been drawing them out is pretty simplistic in this representation. In actuality, neurons have billions and trillions of different connections, okay? So there's lots of connecting parts between one neuron and several other neurons. This is called divergence. This is where the signal splits. All right, so we have this one neuron. Mind you, it's receiving input from several neurons as well, but then the signal or the axon terminal sort of divides off here, and that's divergence. And so we have several different postsynaptic neurons. And then convergence is somewhat the opposite. So this is where several signals, several synapses are communicating onto the soma of this postsynaptic neuron. So we have many presynaptic neurons synapsing on to one postsynaptic neuron, okay? And this is just to help us really understand the big picture. So neurons aren't speaking one-on-one, it's not a one-on-one conversation, right? It is multiple conversations, multiple synapses, multiple transmission of these electrical and chemical signals, okay? Let's review summation. Again, we talked about summation before, this ability of graded potentials to sum or to add at the axon hillock, okay? And we can add or sum different types. So we've spoken about IPSPs and EPSPs, and because they are graded, they can be summed, okay? So let's consider the two types. So let's look at this first neuron, and we put our voltmeter in the axon hillock because that's where we want to measure the membrane potential change at the hillock. That's what's going to determine whether or not an action potential is propagated. So this is the area that we really want to be picking up the voltage. So we're looking at the voltage of this postsynaptic neuron, and we're trying to decipher if we get to that threshold to fire an action potential. Now we have 3 different neurons synapsing on here. We have 2 EPSPs and 1 IPSP. And so the summation happening here is spatial, okay? I'm sorry, it's temporal, so it's happening in time. So basically, one synapse, and we're summing all the synapses that happen, or all the events that happen at that very same synapse, right? Let me say that again. So we're only looking at synapse A, but we're looking at synapse A in time, okay? So this is temporal summation. So if synapse A fires one graded potential, let's say within enough of a period of a time that we can sum these, we fire another graded potential. Those two EPSPs in this case will combine and we will get enough of a threshold stimulus to fire an action potential, okay? Spatial summation is a bit different. We're taking into account all the neurons synapsing onto the soma. And so we look at A, B, C, and we basically combine them, and then we determine if we get to a threshold stimulus. So we can sum graded potentials in space or in time. Okay, let's talk about frequency coding. Now, frequency coding is the degree of depolarization at the axon hillock. So again, because we cannot grade action potentials, because there's not a small action potential versus a medium action potential or a large action potential, the way that we can appreciate, or the way that the nervous system appreciates varying degrees of a stimulus is by increasing or decreasing the frequency of the action potentials. And so this happens at summation as well. So these are the things that we are analyzing at the axon hillock: the frequency of the action potential to determine if it's a strong stimulus or a weak stimulus. We're looking at the number of action potentials to see if we can sum them and the number of graded potentials to see if we can sum them and fire an action potential. And so these are the different things that are happening at the axon hillock, okay? And this is what neural integration is: determining whether or not all of these different parts, all of these different signals that are coming in, right? This image really highlights what's going on a soma. Lots of different IPSPs, EPSPs, we have membrane stabilizing events, and we need to sum those together at this location and decipher whether or not we qualify, so to speak, for an action potential. And if we have more action potentials here, in the case of frequency coding, we release more neurotransmitter, and this registers as a greater signal, as a greater response, okay? All right, let's talk about presynaptic modulation. Now, presynaptic modulation is another way of regulating this transmission. It uses an axon arrangement that we spoke about. We talked about axoaxonic synapses, and this is where the two axon terminals on two adjacent neurons are communicating. And this is the rare instance in the body where we see these types of connections, okay? And this is going to be modulating an axodendritic connection. All right, so basically we have an axoaxonic relationship here, but it is modulating or influencing an axodendritic connection. Very important to make that distinction. So you may see a question that asks about what type of connection is a modulating neuron, right? It's axoaxonic. What type of synapse does a modulating neuron regulate? It's an axodendritic. Okay, so the synapse itself is axoaxonic, but it's influencing an axodendritic synapse. All right, enough rambling. So this can either facilitate or inhibit the axodendritic synapse. And basically, it is going to influence how much neurotransmitter is released. So this has nothing to do electrically. It's not stimulating any any electrical energy. It's not firing an action potential. It's not influencing the membrane potential change. Very, very important to understand that. All it's doing is it's influencing this other neuron here, which is the presynaptic neuron, to either increase its contents or decrease its contents, okay? Let's look at an example here. So let's look at presynaptic facilitation. So this is increasing the amount of neurotransmitter that's released. And so we have this axon here. We have 3 neurons stimulating here. We have an axodendritic relationship, an axodendritic, and this is an axoaxonic, okay? And so neuron E is simply facilitating the release of neuron C. It's not influencing the postsynaptic potential here. It's not generating any membrane potential change. All it's doing is it's telling neuron C to secrete more neurotransmitter, okay? And so if you look at the change in the membrane potential, again, we're looking here at the axon hillock of the postsynaptic neuron, and we're looking at the membrane potential change. We can see that neuron C on its own generates a small graded potential. Neuron D on its own generates, again, a small sub-threshold graded potential. Neuron E has no influence on the membrane potential, so no electrical energy as such here on its own, okay? But adding neuron C and E automatically brings us to a threshold stimulus, and we qualify to fire an action potential. And in such a way, neuron E is kind of like a helper of neuron C, and it's just sort of nudging it to secrete more neurotransmitter. Okay. Likewise, for presynaptic inhibition, we have two neurons against synapsing onto this axon, soma, and neuron G on its own gives us a subthreshold stimulus, as does neuron F. But if we take into account neuron H on its own, no change in the membrane potential. But if we combine neuron F and G, right, we have a subthreshold stimulus. But if we look at F and H, right, H is basically telling neuron F, secrete less neurotransmitter. And so it becomes hard to fire an action potential here, because we have this modulating neuron that's discouraging, I want to say, right, preventing, inhibiting that second neuron from secreting as much neurotransmitter. And so it's sort of halting or delaying or interrupting the signal, making it harder to fire an action potential. And so this is how we can modulate or regulate the different synapses. We can increase them, potentiate them, turn them on with these modulating neurons, or we can decrease them or decrease the amount of neurotransmitter. Now, it's very important to make the distinction here that these modulating neurons are offering no electrical activity here. They are actually influencing the amount of calcium that is being uptaken on that second neuron. So we spoke about the synaptic events, and we said that calcium has to rush into the axon terminal in order to influence the exocytosis of that neurotransmitter. So if we rush a lot of calcium in by opening up lots of voltage-gated calcium channels, we secrete more neurotransmitter. If we open up less voltage-gated calcium channels, less calcium goes into the terminal bouton, we secrete less neurotransmitter.